Welcome to your third electrochemistry video. Today we're going to talk about cell electromotive force. Sounds pretty fancy. So first let's define volts. So a volt is the potential difference required to impart 1 joule of energy to a charge of 1 coulomb. In other words, a volt is 1 joule per coulomb. 1 electron has negative 1.602 times 10 to the negative 19 coulombs. So this is a cool little number to know. And EMF, again, it stands for electromotive force. And this is what moves the electron through the external circuit. E cell. And E cell is called the cell potential. That's really the key thing you want to get out of here. E cell. We're going to be calculating E cells or cell potentials. You'd want to know that any spontaneous reaction will have a positive cell potential. So if it's going to be spontaneous, then the cell potential must be positive. For example, a zinc copper cell, so a cell, sorry, my cat's going to be meowing a lot today probably. So anyway, you have a cell that has zinc on one end and then copper in ion form over here, bloop, 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 and they're connected by a wire. So this zinc copper cell potential is plus 1.10 volts. So we're going to be assuming that these guys are happening in standard conditions. So remember, standard conditions are 1 atmosphere, 25 degrees C. It's basically like room temperature and pressure. And this is also assuming that we have one molarity, so the concentration of 1 for reactants and products in solution. These numbers give us these standard reduction potentials, these standard numbers. They're in a chart. You would never have to memorize them. What's kind of blocked off here is that they would come off of an equations sheet or some sort of just given piece of paper that has all of these numbers. And one of the ways you can calculate the cell potential would be to take the standard cell potential of reduction of whatever is the cathode minus the standard cell potential of reduction of the anode. So in other words, if you look at these equations, they're all reduction half reactions, and if I have a copper zinc cell, notice how these half reactions are both showing a gaining of electrons, which is reduction. We know in reality when you have those two different beakers, one of them actually has oxidation occurring while the other one has reduction. And that's okay. This equation takes that into account. So even though we're using numbers that both represent reduction, it's fine. You just plug them in. Don't worry about it. You'll notice that zinc, which is usually oxidized, has a negative reduction potential. That means that it is not very likely to be reduced. It's more likely that it will be oxidized. Whereas copper has a positive reduction potential, so it is likely that it will actually be reduced. It's unlikely that it would be oxidized. So here's that chart again. As the reduction potential increases, you increase the ability to attract electrons. So silver is better at attracting electrons than aluminum is. And then as you go down here, again, you are increasing their ability to lose electrons. It's easier for aluminum to lose electrons than it is for silver to lose electrons. So a reduction half reaction is the measure of the tendency of the reduction to occur. So just like I was saying, the more positive this number is, the more likely it is that it will be reduced. Fluorine, F2, has the most positive reduction potential. It'll be at the top of your chart. It is the most likely substance to be reduced. It is the strongest oxidizing agent. If you remember on your periodic table, fluorine's on the top right. It really, really wants those electrons really badly because it's so close to being like a noble gas. And then lithium actually has the lowest but still positive reduction potential. So it's the least likely to be reduced. It's the strongest reducing agent. It is very unlikely that it would be reduced. Something that's nice to know is coefficients do not matter. We don't care about coefficients when we're calculating cell EMF. So this equation up here, going back a couple slides, nope, not that one. Here we go. This equation here, you might want to, oops, give yourself a little note that says, oh my gosh, what am I doing? Come on. There we go. Coefficients don't matter. You can ignore them. They don't matter. Coefficients do not matter. That makes our calculations a lot simpler. So, and I've kind of mentioned this before, that if the cell potential is greater than 0, then it is spontaneous. So, you know how Gibbs free energy, if that is less than 0, it's spontaneous? Well, if the cell potential is greater than 0, it's spontaneous. So don't mix those up. You need to know that they are opposites there. Greater than 0 is spontaneous. So we have something called a standard hydrogen electrode, and if you were to create an electrode of hydrogens, you could say, oh, that has a reduction potential of 0 volts. So you know how scientists like to base a lot of things off of water? Like the density of water, you know, being 1, which is really nice. So when scientists were deciding on voltage, what they did was they figured out hydrogen. They said, okay, that one's going to be 0, and then it was a reference point for all of the other reduction potentials that were determined. So hydrogen is our reference point here, a standard hydrogen electrode. Okay, the rest of this video is going to be practice problems with a slight bit of notes at the very end. So stick with me here. What is the cell potential for a voltaic cell that has nickel at one electrode and copper at the other? And then is it thermodynamically favorable or not? And the cells are under standard conditions. Okay, so what you need to do is say, okay, we've got nickel and copper. Well, which one is being reduced and which one is being oxidized? Because remember, our equation is going to have the reduction potentials for both of them. They're both reduction potentials. But the one that comes first is for the thing that is actually reduced. It's for the cathode. And the one that comes second is the one that is at the anode, so the thing that's being oxidized. So we need to figure out between nickel and copper which one is more likely to be reduced, and that one will come first. So go back a couple slides, find this image here. Let's see, copper, whoops, here's copper, and there's nickel. So which one is more likely to be reduced, copper or nickel? Copper is more likely to be reduced because it is positive. So copper is going to come first in our equation and nickel will come second. So I'm going to take these numbers and go back to my other slide. Positive 0.34, negative 0.25. Remember those. So I'm going to say, all right, since copper is being reduced, nickel is being oxidized, I need to take 0.34 volts minus negative 0.25 volts. So it's the thing that's being reduced minus the thing that's being oxidized, the cathode minus the anode. And this number will come out to positive 0.59 volts. Okay, cool. So the trick on these problems really is figuring out what's being reduced and what's being oxidized. What's the anode, what's the cathode? And you can figure that out multiple different ways. This is one of them. Now, obviously the answer is right here. It says, yes, it is thermodynamically favorable. How do you know it's thermodynamically favorable? Because the standard cell potential is positive. That's how you know. Simple as that. Okay, let's try another one. For the zinc copper voltaic cell, the standard cell potential is 1.10 volts. If the reduction potential of zinc 2 plus to zinc is negative 0.76 volts, calculate the standard cell potential of reduction for the reduction of copper 2 plus to copper. Oh, all right. So they gave us the reduction potential of zinc, and they're asking us to figure out the reduction potential for the reduction of copper. So the question here is, in our little equation, they gave us the total, 1.10 volts. What is being reduced and what is being oxidized? Well, they're telling us it's for the reduction of copper 2 plus to copper. So they're telling us, oh, copper is the thing that's being reduced. So that is the one that will go first or second? It would go first. This would go first. So of copper minus the reduction potential of zinc, which is negative 0.76 volts. And hey, it makes sense that zinc is the one that's being oxidized because based off of this negative number, does it really want to be reduced? No, not really. Zinc, you could say, prefers to be oxidized. So this order makes sense now. Okay, so let's see, -2 negatives, that becomes positive. Now I'm going to subtract 0.76 volts from both sides. And I will end up with, for copper, a reduction potential of 0.34 volts, positive. Okay, that's another type of problem you could run into. All right, well, what if they said, determine the value of the standard cell potential for a voltaic cell operating on a reaction between silver nitrate and solid nickel? So again, you need to figure out what is being oxidized and what's being reduced. And these two things that I've underlined are what tells you that. These will be the answer to that question. So try drawing a little quick picture here. We know one of these is going to have solid nickel. There it is. Solid nickel. And the other one is going to have silver nitrate. Silver and nitrate. So here we're starting off with solid nickel. Here we're starting off with silver as an ion. So if I was going to write my half reactions, nickel is probably going to do what with electrons? Is it going to gain electrons and become a negative nickel ion, or will it lose electrons and become a positive nickel ion? It'll most likely lose electrons. I don't know how many electrons nickel usually loses, but regardless, it's probably going to lose them. I don't know, I guess I could check. Here, let's go back. Nickel, 2. And silver most likely will gain that electron, and it'll gather up as a solid silver over here. Okay, so which one is being reduced? Because that's the one that's going to come first in our equation. Reduction is gaining, so silver is being reduced. Okay, so remember, the cell potential is going to be the reduction potential of what's being reduced, so the cathode, silver, minus the reduction potential again, but this time for what's being oxidized, the anode, which is nickel. So now I need to go back to my chart and find those numbers. Silver, here it is. Oops. There's silver, and nickel, I've already got it over here. There it is. So I'm going to take these numbers down. 0.80 and negative 0.25. Okay, so silver comes first, so I'll have 0.80 volts minus a negative 0.25 volts, and hey, we end up with plus 1.05 volts. This is our standard cell potential. Neato. Let's move on. Okay, another one. So again, the trick here is figuring out what is being oxidized and what's being reduced. So, it's a scary equation. It's designed to scare you. Don't let it happen. So they are giving us the reduction potential here for our chromium. There it is. Positive 1.33 volts. So does chromium like being reduced? Yes, it looks like it does. All right. Hydrogen, does hydrogen look like anything's happening to it? No, it looks like it's positive, positive, 1, nothing there. What about iodine? Iodine started off with a charge, and then it ended up with no charge. And I know that because when it forms this little diatomic molecule, I know that it's got to have an oxidation number of 0 in order to be neutral, which it is. So did iodine gain electrons or lose electrons? Iodine lost electrons, which means, was it oxidized or reduced? Oxidized, which means that our chromium, without having to do any really complicated work, was most likely reduced. I mean, you could check it if you would like to. You can. I believe it goes from a 6 plus charge to a 3 plus charge. We did this in one of the previous videos. But regardless, we know that well, let's look up the iodine number and then we'll figure out which one will come first. So for iodine, it's plus 0.53. So E reduction for iodine equals plus 0.53 volts. So we have our two different numbers here, this one and this one. Which one is going to come first? The one that belongs to whatever is being reduced will come first. The cathode comes first. So in that case, it is 1.33. 1.33 volts minus a positive 0.53 volts, and you'll come out with plus 0.80 volts. So is this process thermodynamically favorable? Yes, it is, because it is positive. So really the trick is figuring out what's being oxidized and what's being reduced. Once you can get over that hump, then you're good. So using the standard reduction potentials, calculate the standard EMF for the voltaic cell described below. Aluminum reacts with iodine to form aluminum and iodide ions. So this would be a really good opportunity for you to try this out without me. So pause and figure it out. Go ahead, go, do it, pause. All right, welcome back, those of you who actually paused. What you need to do is say, okay, aluminum became an ion. It became more positive. So in order to go from here to here, aluminum must have lost electrons, which means it was oxidized. I like to do this at the top of my paper, or you could do this. Whatever works for you. All right, so if that's the case, that means that iodine, that went from 0 to a negative charge, so it gained electrons. So this one was reduced. I should probably label this as oxidized, so that's the anode. Reduced is the cathode. Okay, so which one's going to come first? Well, that's whatever is the cathode, so that means iodine comes first, aluminum comes second in my equation, iodine minus aluminum. So I'd have to go to my chart, which is back a couple of slides, and I'll say, all right, 0.53 volts minus a negative 1.66 volts gives me 2.19 volts. Cool. I hope that went well for you. Let's try one more. A voltaic cell is based on the following two standard half reactions, cadmium and tin. Determine the reactions that occur at the cathode and the anode and the standard cell potential. So you have to figure out what is most likely to be the cathode and what is most likely to be the anode. That requires you to go out into the wild web and figure out what these reduction potentials are, because they're not on your chart that was earlier in these slides. So why don't you try this one out on your own again? So pause, look up these numbers, and solve this problem. Go. And welcome back if you actually did that. If you did, I'm proud of you. Good job. If not, for shame. So cadmium, you would have gotten a negative 0.40 volts is its standard reduction potential, while tin has negative 0.14 volts. So neither of these guys are too thrilled about being reduced. But one of them is more likely to be reduced than the other, the one that is more positive than the other, which would be tin. So this is going to be my cathode, and that'll be my anode. So now I need to find my standard cell potential. It's cathode minus anode. So take negative 0.14 volts minus a negative 0.40 volts, and you end up with a lovely little positive number of 0.26 volts. So I know the answer was down there, really tempting to look at, but hopefully the reasoning behind this makes sense. Whatever is more positive is more likely to be your cathode. So again, just a quick review. If your standard cell potential value is positive, it is thermodynamically favored. It will happen in that direction. If it is negative, then it's not thermodynamically favored. It won't happen all on its own. You have to do work or add energy or something to make it happen. And the equation that you need to be able to use is right here. It's the reduction potential of the cathode minus the reduction potential of the anode. Okay, last one. A solution of barium sulfate reacts with solid lead. Predict the products. Is the reaction thermodynamically favorable? So, looking at this, which one of these is most likely to be reduced? It looks like... Oh, wait a second. Well, okay, lead is more likely to be reduced. So, usually we'd expect that. However, they're telling us we've got a solution of barium sulfate and solid lead. So, draw that little picture. I almost got tricked. So, solid lead. Here's my solid lead. So my equation is going to start with Pb, which means it's going to have to react to form Pb2 plus and 2 electrons. And here we had barium sulfate in solution. So that means it's starting as barium as an ion. It's going to add on its 2 electrons and form solid barium. So they're telling us with this wording up here, ooh, did not mean to cross that out, a solution of this and solid that, they're telling us what is the cathode and what's the anode. So based off of what I've drawn up here in these half reactions, what is the cathode? What's being reduced? Reduction is gaining. Barium is being reduced. It is our cathode in this hypothetical situation, which is not what it wants to do. But that's how we set it up. So knowing that, let's use our equation. So we want the cathode minus the anode. So negative 2.90 volts minus the anode, 0.13 volts, and we end up with this large negative number. So, is this thermodynamically favorable? No, it's non-thermodynamically favorable because it is negative. And does that make sense? Well, yeah, it does make sense because in this situation, when you have lead and barium sitting together like that, lead is the one that wants to get reduced while barium really wants to be oxidized. You can say wants in quotation marks. Wants to be oxidized, while this one wants to be reduced. So the way that this person set up this lab was going against the nature of these elements. All right, well, that's the end of this video. Hope it helped.